So next, let's consider what happens when we want to find the center of mass for an object of uniform density. We looked at center of masses for objects that had just like discrete points in the last video, but suppose we have like a thin sheet of metal that had the same density throughout. Even though it has the same density, all of the moments are going to be different because the distances from the axes change. And to start off with, this is x. I'm going to look at trying to find what is m sub y. So I want to know if I think about for any individual place on this uniformly dense sheet of metal, let's say, because it has a different distance from the y-axis, it's going to have a different moment. And so we're going to have to consider all of these moments sort of continuously as they go across this sheet. Thankfully, we have techniques that talk about that, right? That if I were to think about splitting up this sheet into uniformly thin strips, for any one given strip, write one strip in red. This is my x sub I strip. We could approximate the moment for this one strip to be uniform across that strip because the difference in distances from the y-axis is really pretty minimal because the strip is so thin. So if I'm looking at the moment just for this one single strip, so I'll call it m sub I because it's a red strip, what's that going to be? Recall before that it was going to be the mass of that strip times the distance that strip has from the y-axis. So this is the mass times the distance from the y-axis, which is just going to be its x-coordinate, x sub I. So what is the mass of this object? Well, how much it weighs? All that we're given is the density. So maybe I should say up here that let's say the density is given by, it's standard to say that use the Greek letter rho to stand for density. So density times area is going to be equal to mass. Because a density is a measure of how much stuff is in something. So we want to know how much stuff is in that something, and then how much stuff is there. So this is my density, and this is my how much is stuff in there, how much area does this taking up. This is the taking up an area, a height of f of x, and a width of delta x times x sub I, because this is my area. So altogether, the density times the area, I'm using area because we're assuming that this object is really close to flat. Really, it should be the volume of the object. Pretend that it's like universally thin. This whole thing together is a measurement of the mass. So all of this looks sort of complicated, right? But it boils down to something relatively simple, that the moment for the ith strip is going to be the density of that strip times the height of the strip times the width of the strip times the distance of the strip from the y-axis, which is given by x of I. But we don't want it for one strip, we want it for all the strips. And this is where we use calculus again, and this is the thing that we've done over and over and over again, that we want to add up every single one of those strips, and we're going to let the limit of the strips, the width of each of the strips, go to 0 as we have infinitely many strips, and that means that the total moment with respect to y for the entire system is going to be the integral from a to b, where that's the starting strip and the ending strip, times the mass, because this will have to be some number like 12. It's a number that's given, times f of x times x dx, where in my head I'm thinking to myself that this is the density of one strip, this is the height of one strip, this is the width of one strip, and this x is measuring the distance to the y axis, that x is this distance here. But recall, just because I found my moment, I haven't found the center of mass, just like we saw before that my center of mass is going to be my m sub y divided by the total mass of system. So we still need to compute our total mass. What is our total mass in this case? Our total mass is going to be the total surface area times the density. So that's going to be the density times how much area there is in this entire object. Well, how do I know how big the object is? It's just the area under this curve, the integral from a to b of f of x dx. So my x-coordinate, maybe I should write it, x-coordinate of the center of mass is going to be given by m sub y divided by m. And we just decided that m sub y is equal to the integral from a to b of the density times the function times x dx, all divided by the integral from a to b of the density times f of x dx. And again, it might be tempting to try to simplify this, but really this doesn't simplify, that the quotient of two integrals isn't the integral of the quotient. Just like quotient rule and derivatives, you can't just pretend that it's each of the derivatives of the pieces on top of one another. You can't just combine these integrals. So what about a center of mass? So this is only the x-coordinate, right? We want to find the y-coordinate also. And we can do that doing the exact same method. And I'll go through it a little bit more quickly. So in this case, though, instead of breaking up our strips vertically, we're going to break them up horizontally. And it makes sense because each strip is going to have a center of mass, or it's going to have a moment dependent upon how far away it is from the x-axis. So if we pick out one strip in particular, for this strip right here, we know that, maybe I'll even write it in red, m sub x sub I is telling me my moment for this ith strip, maybe ith strip right here, and it said y sub I is going to be equal to the mass of the strip times the distance from the x-axis, which is y sub I. And just like before, the mass of the strip is going to be equal to the density times the area of the strip. In this case, this region is bounded by two different functions. You could see in the previous case that that might be the case, but the height here is the larger function minus the smaller function. Here I have them labeled as the top function and the bottom function. So the height in this case is t sub y minus b sub y. So this is the height of the strip. And I say height sort of in, sort of in quotes because the height is laying on its side. You know, I still have a really x-first perspective. The height of the strip times the width of the strip, which is delta y. And so that's the mass of the object, and I need to multiply that by y sub I. And we're going to sum up all of these over the entire interval, and it gives us this integral. M sub x is going to be equal to the integral, I guess we have the same as from y equals a to b, of the density times the height, and in this case we're using functions top minus bottom, times y, which is the distance away from the x-axis, dy. And if we wanted to find the y coordinate of the center of mass, that's going to be our moments divided by the total mass of the system, and the total mass of the system hasn't changed. But I guess I'll rewrite the integral as well. T sub y minus b sub y times y dy, all divided by the mass of the system. In this case, it's the integral, and we're going to have to do the difference of curves because it's going to be the integral from a to b of the top curve minus the bottom curve dy. But we also have to multiply by the density because this is the area times the density gives the mass. I think I'm going to do an example. If you don't want to see an example, you can go ahead to the next video, but I think that it might be helpful to see this put out into practice. Let's say that we want to find the moments m sub x and m sub y. Oh, when I wrote this, it sort of looks like an ordered pair. That's not really what I meant. It's not an ordered pair. And the center of mass of the lamina of uniform density rho occupying the region underneath the graph y equals square root of x. So here's the graph, y equals square root of x, and above the graph y equals x squared. So let's go ahead and think through this and follow some of our formulas. That we're going to start off first by finding m sub y. Recall that this is the moments with respect to the y-axis, so I'm thinking of splitting it up with vertical laminas. For these vertical laminas, I guess our density we're just going to leave as rho. We aren't going to use that as a value. Anyway, so in this case, maybe we do want to find the intersection point of these two curves happens to be at the point 1, 1. That's the place where x squared is equal to the square root of x. You can do some algebra to set those equal, or you could graph them and know that their graphs intersect at 1, 1. So it means that I'm going to integrate from 0 to 1 of the density times, in my previous formula I just had f of x, but really that f of x is standing for the height, and in this case I have to be careful about the fact that I have a difference of heights to get this area under the curve. So it should be the top function, which is square root x, minus the bottom function, which is x squared, times x dx. This ends up being a straightforward integral, although it'll take a little bit of computational power to do it. I can follow power rule. This becomes rho times the integral from 0 to 1 of x to the 1/2 minus x squared times x dx. I'm going to do the distributive property and get rho times the integral from 0 to 1 of x to the 3/2 minus x cubed dx. I'm ready to integrate. Following power rule, I add 1 to the exponent and get 5/2, then multiply by the reciprocal, 2/5, minus adding 1, I get 4 to the exponent, multiply by the reciprocal, 1/4. And I'm evaluating this as x goes from 0 to 1. Those are nice bounds, because I can do this actually in my head. Plugging in 1, I see that I get 1 to the 5/2 times 2/5. That's just 2/5 minus 1/4 minus the lower bound, rho times, plug in 0 and I get 0 minus 0. Hooray! And this is just fractional arithmetic. So what is this? This is 2/5 minus 1/4. I can do these as 20ths. So this becomes 8/20ths minus 5/20ths is 3/20ths. And hopefully my fractional arithmetic is correct. So that's the moment with respect to y. Let's do the moment with respect to x. Now we have to do a little work though, and maybe I'll even write this in red. So now we're examining the distance to the x-axis, and so we have to do our curves this way. It means that our integral, in this case, my bounds are in terms of y, from y equals 0 to 1. Maybe this is a poor example because my bounds are the same with the x and the y-axis, but that might not necessarily be the case. The other tricky thing that happens is that I need to resolve these curves, that this curve over here is the curve y equals square root of x. That's the same thing as y squared equals x. Also, solving for x for this one becomes x equals the square root of y. Why am I doing this? This integral is with respect to y. It's rho times the difference in heights times y dy. And the difference in heights, I can't have the difference be in terms of x functions. I have to rewrite these functions in terms of y functions. And finally, I need to decide, well, which is the upper function? The upper function is the function that's further away from the y-axis. And so in this case, the upper function is the function y equals x squared, but I don't want it as a function of x, I want it as a function of y. So I write it as the square root of y. And I need to subtract the next function, which is the bottom function, which is this. Similarly, I can simplify this. So this is the integral as y goes from 0 to 1 of rho, and I'm going to multiply this all out. This becomes y to the 3 halves minus y cubed dy. Haha, this looks surprisingly similar. When I integrate, I get rho times raising by 1. This is y to the 5 halves times 2/5 minus y to the 4th divided by 1/4. I evaluate it as y goes from 0 to 1. And notice that because of the symmetry of this function, I end up with the exact same value. And that makes sense because although this picture looks a little sloppy, this region is symmetric about the x and the y-axis. So now that I've found each of the moments, I still have to compute the center of mass. So I'm going to compute the center of mass for the x coordinate is going to be my divided by, oh, I didn't compute the total mass yet. Maybe I'll get another sheet of paper. Let's find the total mass of the system. The total mass of the system, m. And really I could do it with respect to x or with respect to y, either way. I like doing integration with respect to x, so I'm going to go, and really we're just finding the area between these two curves and multiplying it by the density. So what's the area between these two curves? The upper curve is the curve square root of x, the lower curve is the curve x squared dx. Finishing this integration, I can pull the rho out front, and I get the integral from 0 to 1 of x to the 1/2 minus x squared dx. Let's integrate, and I get x to the 3/2 times 2/3 minus 1/3 x cubed, evaluated from 0 to 1. When I plug in 1, I get 2/3 minus 1/3. Nice, I can do that in my head. Minus rho times 0 minus 0. Evaluating at the lower bound, I just get zeros. So it means that my total mass of this object is rho times 1/3. Whew! So that means the center of mass for the x coordinate is going to be m sub y, right? Because m sub y is showing how far over in the x direction it is. M sub y divided by m, which in this case m sub y was 30/20 times rho divided by 1/3 of rho. And then the center of mass of the y coordinate is m sub x divided by m, which is the exact same value. Notice that the rows cancel, and I'm dividing fractions, so this is multiplying by the reciprocal. I get 3/1, so this is equal to 9/20, and it's also going to be 9/20 for the other coordinate. Notice that these are unitless because these are coordinates. This is a place, a location in space. This is an x coordinate and a y coordinate, and I can write the center of mass as the ordered pair 9/20, comma 9/20, which 9/20 is a little less than halfway over. And I might mark it with an X. So for my final thing in this video, I'm going to show a clever way to be able to integrate with respect to x. So before, when we were finding our moment with respect to x, with respect to the x-axis, we split it up horizontally in these horizontal strips and had to integrate with respect to y. Sometimes that's a hassle, so we're going to do it a way. This is our method number 2. And if you like method number 1, it'll work for a lot of problems, but maybe not all of them. So our tricky way, before, when finding our moment with respect to the x-axis, we made horizontal strips. For our method 2, our new way, we're going to make these vertical strips instead. And we're going to use the fact that because the density is uniform, instead of considering the entire strip, we're just going to look at an average. So the moment for this strip can be computed by looking at the center of the strip, because that's an average of the top and the bottom, and moments are a linear function. So, what did all that say? It means that if I want to look at the moment for this j'th strip right here, highlighting this strip right here, with respect to the x-axis, I can consider what's going on with the midpoint of this strip. That the moment with respect to the x-axis of the j'th strip is given by the mass of that strip times the distance, the height y, because that's the distance to the x-axis. Like normally that's how that works, but what is the height y? That doesn't really make sense because this is a variable height. We're going to find the average height of the strip. And in this case, the average height of the strip is easy to find. It's right in the center. So that means that this formula can be given by the mass is the density of the strip times the height of the strip times the width of the strip. So this is all the mass. This is density. This is height. And then this is width. And then we're going to times it by the y coordinate, but really what we mean is the distance from the x-axis. And so we're going to look at 1/2 f of x sub j. Why does that make sense? Because 1/2 in this case is the distance from 0 up to the top of the function. It's the midpoint of this strip. So this is the midpoint distance to the x-axis. And this is nice because now my formula simplifies slightly. It means that I can rewrite my formula for m sub x as the 1/2 I can pull out, the density I can pull out, that's also a constant. I integrate from a to b of f of x. Notice I have x sub x sub I and f of x sub I over here. I guess all of these should be i's and not sort of a combination of i's and j's. Squared dx.